Today I will introduce the basic concepts of probability theory. So, probability theory had its origins in the games of chance in early 16th and 17th century, when the owners of gambling houses in Europe, they became interested to explore that whether one can find out the probabilities of various events which take place during a gambling game, such as tossing of dice, rolling of coins, roulette wheels, etc. So, they contacted some of the prominent mathematicians of that time, say Pascal and Fermat, and through the correspondence between these mathematicians, the theory of probability started to develop. One of the fundamental features of this probability is that the phenomena which we are interested in are random in nature. So, for example, if you consider tossing of a dice, then we do not know whether which face bearing number 1, 2, 3, etc. will come. But in the long run, if we toss enough number of times, then the proportion of the number of occurrences of say one of them, say 6, will be 1 by 6, say, then it means that the probability or the chance of appearance of 6 is 1 by 6. Similarly, in the tossing of a coin, we do not know that at each trial whether we will get a head or a tail, but if we toss a large number of times, then we know that nearly 50% of the times there will be head, or 50% of the time there will be tail. This long term behavior is known as statistical regularity, and that is what encourages us to study the subject probability. A similar kind of observation you can make in the experiments which are connected with the real life, such as experiments in physics, experiments in genetics, or virtually any phenomena in real life. Consider, for example, birth of a offspring. Now, suppose we consider human beings, then for each birth we do not know whether the child will be a boy or a girl, but in the long run it is very well known what percentage of children will be boys and what percentage will be girls. A insurance company, while promoting a new policy, would like to know how many of the people will survive up to the age of maturity. For example, if the policy matures at the age of 60, then it would like to know the percentage of the people in the target group who will be surviving beyond the age 60 and therefore may get the benefits which are due to them. Now, for individual person it is not possible to tell whether he will die at the age of 60 or not, but in the whole population one can tell the percentage of people dying before 60 or dying after the age of 60. A similar kind of statistical regularity is observed, and it is used for weather predictions, the prediction of the, say, growth of crop, the economic growth, the financial situation of a country, etc. Here what happens that in most of these cases, although the things may look that they are preordained or predesigned, but predetermined, but actually there will be several conditions which regulate the occurrence of the final phenomena, and therefore one can treat them as random phenomena. Now we will introduce some of the basic concepts. The first is experiment, the term which I have used repeatedly just in the discussion. So, an experiment is observing something happen are conducting something under certain conditions which result in some outcome. Let me explain this little vague definition. So, consider say rainfall. So, now rainfall is a consequence of several things. Finally, we observe that there is a rainfall. So, there is a cloud formation, there is some El Nino currents, there is a humidity, there are various factors which lead to there is a rainfall, or there it is cloudy, or it may not rain at all, it may rain in some other region. Now, observing of this weather is a experiment. Similarly, suppose we consider how much crop of a particular, or how much yield of a particular crop, say wheat is there in a particular field. Now, this is dependent upon the seeds, the plot of the land where it is there, the irrigation procedure and other mechanical procedures which are used for farming. So, the entire process, although we are not conducting, but it is happening and it is a random experiment. The outcome is recorded as the final yield of the crop. You must be very well familiar with a lot of experiments which are done in physical, chemical and biological sciences. For example, we have various experiments in chemistry where certain chemicals are mixed and they result in some compound being made. So, broadly speaking, we segregate the experiment into two types of experiments. One is deterministic experiment. In the deterministic experiments, under certain conditions, if an experiment is conducted, it results in a known outcome. So, many of the classroom experiments in physics, chemistry, biology, etc., they are like this. For example, if I have two molecules of hydrogen and a molecule of oxygen, then we know that the outcome is a water. Suppose we consider say we put water in a vessel and heat it, when the temperature reaches 100 degrees Celsius and the atmospheric pressure say 700 mg, then the outcome is that the water will boil. So, these experiments are called deterministic experiments. However, we are not concerned with these experiments in this subject of probability. We are concerned with the experiments which are called random experiments. In the random experiments, although we may fix the conditions under which the trials are conducted or the experiment is conducted, but the outcome is still uncertain. Consider, for example, tossing of a coin. So, although we may fix a lot of conditions such as what kind of coin we are having, how to hold it when we are tossing, but even then when we toss the coin and it falls, the outcome is uncertain. It may be head or tail, or in some extreme situation we may consider that it stands on its side also. Consider say tossing of a die. So, again the conditions are similar. We may fix the die in various ways, but when we toss it, and if it's a if we are really tossing it, then after falling which face will be upwards is not known. Suppose we consider drawing of a card from a deck of cards. Suppose we consider, say, birth of a child. Suppose we consider age at death of a person. Suppose we consider, say, amount of rainfall during a monsoon season in a geographical area. Suppose we want to consider yield of a crop of a certain food grain in a state. Suppose we consider the time taken to complete a 100-meter sprint by an athlete. All of these phenomena, here the conditions of the experiment are fixed. For example, when we look at, say, the time taken to complete a 100-meter sprint by an athlete, then the conditions are fixed. For example, the ground is fixed, the starting time is fixed, the athlete is in a perfect condition, the person who will direct the race is prepared, the person who will record the time is prepared. However, how much actual time the sprinter will take to complete the 100-meter race will always be uncertain. It may be 10 seconds, it may be 10.1 seconds, it may be 9.7 seconds, etc. Suppose we are considering, say, a mechanical instrument such as, say, life of a bulb. So, when you purchase a bulb from the market and you light it, then it may work for 1 hour, it may work for 10 hours, it may work for 100 hours. So, although all these bulbs may be produced by the same company under the same conditions, even then the actual life of the bulb is not fixed, it can vary. If we look at, say, working time of a say, life of a mechanical instrument, say, for example, a certain turbine or a certain engine. So, although they are all produced by a certain standard process, but the actual life of that instrument cannot be predicted in advance. We may consider, say, in these cases, all of these examples, they relate to certain fixed conditions for the conducting of the experiment. However, the final outcome is not known in advance. So, all of these are known as random experiments, and in the subject of probability, we are concerned only with the discussion of the random experiments. So, for example, if we why these type of events are of interest. For example, you consider birth of a child or age or death of a person. So, now these phenomena are extremely useful in practical. For example, insurance companies, when they propagate a life insurance policy, they are very much interested that what premium they have to fix. Now, how to decide about the premium? The company charges a premium, and in the case of unlikely case of the person dying before the age of maturity, he has to be paid full benefits of the policy and plus some assured sum. Whereas, if the person completes the policy, and that means he does not succumb before the age of maturity, then he pays the premium till the maturity, and then he gets certain benefits which or not that much as he would have got if the person had died before the age of maturity. Therefore, the company has to estimate how much premium it will be charging and how much will be actually the cost to the company in the event of the death of the person prematurely. So, the age at death of a person in the target group is to be estimated, and therefore, we will record, we keep the records of the ages of the persons in that particular target group for which the company is trying to sell the insurance policy. If we look at the amount of rainfall, then extremely important phenomena, because there are a lot of policies of the government, the policy, agricultural policy, the economic policies, which are based on actual rainfall which is going to be there in the country. The yield of a crop makes the government to decide about how much food grains they are going to purchase from the farmers, how much they are going to store, what should be the price which should be given to the farmers, what should be the price for the market. So, all of these events, the experiments, although they do not look random beforehand, however, outcomes are not known and therefore, they are random, and in the subject of probability and statistics, we do study these type of phenomena. So, now let me introduce certain basic terminologies of the random experiments. The first of this is the concept of a sample space. So, the set of all possible outcomes of a random experiment is called a sample space. The usual notations we will use either capital omega or capital S, etc., to denote the sample space. So, let us consider some examples. Suppose we are considering tossing of a coin. In the tossing of a coin, we may put the outcomes we may consider as head or tail, and if we denote by H the occurrence of head upwards or by T the occurrence of tail, then the sample space can be described as HT. If we consider tossing of a die, then the sample space we may describe as occurrence of the face uppermost. So, the sample space will be the set of the numbers 1, 2, 3, 4, 5, 6. If we are considering a drawing of a card from a deck of cards, now in a deck of cards there are 4 denominations: heart, club, spade and a diamond, and each card has a value 1 to 13. So, if we consider drawing of a card, then it will consist of the set, for example, diamond 1 to diamond 13, club 1 to club 13, heart 1 to heart 13, or a spade 1 to spade 13. So, the sample space consists of 52 points. If we look at, we may also observe the sample space in a way, like for example, we may only record the color of the. So, in that case we may describe it differently. We may call this one as omega 1, and if I am recording only the color, then it may be say black or red, or we may only record the denomination, that is whether it is a heart or whether it is a diamond or it is a club or it is a spade. So, the sample space will consist of only 4 points. This also shows that sample space is not a unique thing. In a given experiment, what we are interested in will decide that what is a sample space. If we are looking at the birth of a child, then it is a vague statement, or you can say a vague way of describing what is a random experiment. Now, we may record whether the child is a male or a female child. We may record whether the child born has is healthy or not healthy. So, we may put it as healthy or unhealthy. We may look at his body weight at the birth. So, the body weight may be some number starting from say 0 to say maybe 10 pounds. It may be the total life of the child, So in that case this may be something like say 0 to 100. So it depends upon that what is our actual interest, and we can write the sample space accordingly. Age at death of a person, so this may be say 0 to say maybe 120, keeping into account that there are some people who live very long, where this unit of the time is years. Amount of a rainfall may be recorded in say centimeters. Yield of a crop may be recorded in some metric tons. The time taken to complete a 100-meter sprint may be a time from say 9 seconds to say 11 seconds. Suppose I am considering an international field. Life of a bulb is a number say which is 0 to infinity, although theoretically speaking it is not infinity, but it can be a large number. Life of a mechanical instrument similarly can be described. Suppose we are looking at the number of defective items produced by a company. A particular kind of items we are looking at, suppose we are looking at certain bolts, then what will happen that we will define the defectives, that if they do not conform to certain prescribed standards of measurement. So now the number of defectives may be recorded in terms of percentage. So the percentage can be say 0 to 100%, or it could be say proportion. In that case we may write the number as say 0 to 1. So the sample space will again be dependent upon the way we want to look at it. Next we define what is an event. An event is any subset of the sample space. Now this is a very broad definition, and therefore any subset of the sample space qualifies to be an event, to be called an event as far as the probability theory is concerned. So let us look at the experiments now and the examples that we have already done. In the first case, if we look at omega is equal to ht, we may consider a subset as consisting of only h. We may consider a subset consisting of say only t. So the set A denotes that head has occurred, the set B denotes that t has occurred. So these are events. We may consider say the set E in the case of tossing of a die, we may write 2, 4, 6. This means occurrence of an even number. In the birth of a child, suppose we are looking at say weight at birth in pounds, and suppose we say E is equal to 4 to 8, then it means that the birth weight of the child is between 4 to 8 pounds. If we look at the amount of rainfall and in centimeter during a particular monsoon season, and we may put say 50 to 75, that means the actual rainfall is between 50 centimeter to 75 centimeters in that geographical area during that particular monsoon season. So any subset of the sample space can be considered as an event. Now we have various kind of events. For example, impossible event. Since every subset is a subset of every event is a subset of the sample space, therefore the empty set phi, that is a subset of omega, therefore this will correspond to impossible event. Similarly we have sure event. Since omega itself is a subset of omega, therefore this is denoting the sure event. For example, we may consider tossing of a die, and we say that 7 occurs. So that will correspond to an impossible event, because 7 is not a subset of this, and that will correspond to phi as far as this random experiment is concerned. Suppose I am looking at the age at death of a person and we say 1000 years, then it is an impossible event. Suppose we say time taken to complete a 100-meter sprint by an athlete, and we may put the time as say 5 seconds. Then in the present circumstances or present age, this is an impossible event. Similarly, if I put that the time taken to complete a 100-meter sprint by an athlete, provided he completes the race, is less than 1 minute, then this will be a sure event. If we look at the life of a bulb and we say it's a positive number, then or a non-negative number, then it's a sure event. So these are two you can say extreme types of events which are possible. However, there are various set theoretic operations like unions, intersections, differences, complementation, and therefore given any two events, when we take their unions, intersections, differences, complementations, etc., they must correspond to certain events, and we can describe them in the form of probabilistic explanation. So, for example, union of two events. So, what does union of two events implies? That if I say A and B are two events, then A union B, this will mean occurrence of at least one of A and B. That means either A occurs or B occurs or both occur. So, in set theoretic representation, A and B, A union B means that the set of elements which are either in A or in B or in both. In probability theory, the event A union B will indicate that at least one of A or B has occurred. Similarly, we may consider union of a n events A1, A2, An. Then this will mean occurrence of at least one AI, I is equal to 1 to n. We may even consider an union of infinite number of events, union AI, I is equal to 1 to infinity. This will mean occurrence of at least one AI, I is equal to 1 to infinity. Intersection of two sets denotes the set of all those points which are common to the two sets. Now, in set theory, that is the representation. In probability theory, A intersection B will mean the simultaneous occurrence A and B. That means both event A and B are deemed to have occurred. Similarly, we can consider intersection of n events AI, I is equal to 1 to n, that is simultaneous occurrence A1, A2, An. That means all of the events A1, A2, An occur, and in a similar way intersection of an countable collection of events A1, A2, etc. Here, when we consider the unions or the intersections, certain basic properties are there. For example, we may have union of AI, say I is equal to 1 to n is equal to omega. That means all the points of omega are contained in one or the other of the AIs. Such events are called exhaustive events. So, if A1 union of AIs is equal to omega, we call A1, A2, An to be exhaustive events. Here in place of n, we may have an infinite collection of events also. Similarly, if A intersection B is equal to phi, now in the set theory this means disjoint sets. In probability theory, A intersection B is equal to phi denotes that the events A and B cannot occur together. They are called mutually exclusive events. A and B are called mutually exclusive events. That means happening of one of them excludes the possibility of happening of the other. We may also consider something like this, that we have a collection A1, A2, etc. of events such that AI intersection AJ is equal to phi when I is not equal to j. Then we say that A1, A2, etc. are pairwise disjoint or mutually exclusive events. Given an event A, the A complement will denote not happening of A. In a similar way, if I have event A and an event B, then A minus B will denote happening of A but not of B. This is true because this is equal to A intersection B complement. That means simultaneous occurrence of event A and B, which means that A occurs and B does not occur. So, it is a simultaneous occurrence of A and B complement, and it is translated to occurrence of A but no occurrence of B. Based on this, we give the first, or you can say a primary definition of probability. It is called classical or mathematical definition of probability. This definition is due to Laplace, which was available in his treatise on probability in 1812. Now, this is based on certain conditions. I have already introduced the concept of several events. So, these are all subsets of the sample space. We may call events say A1, A2, AN to be equally likely. Now, this is some terminology which is like circular in nature. Let me again explain. So, I will say events A and B are equally likely if A and B have the same chances of appearing. Now, till now we have not defined what is a chance. So, this definition itself looks circular, but anyway, this is what has been used in the classical definition of probability. Suppose a random experiment has n possible outcomes which are mutually exclusive, exhaustive and equally likely. So, that means we are looking at the elementary outcomes of the random experiment which are collected in the sample space. That means the sample space has a total of n points, which is a finite number, and naturally then when we are describing all of them, they are supposed to be mutually exclusive and we have exhausted all the possibilities. So, I am making an assumption that they are equally likely. Let m of these outcomes be favorable to the happening of event A, then the probability of A is defined by probability of A is equal to m by. So this definition was given by Laplace because of the earlier statements which I gave, that the probability theory has origin in the games of chance, such as tossing of a coin, throwing of a die, the numbers coming on a roulette wheel, etc. So all of are drawing of a card in a pack of cards. So all of those experiments had a peculiar thing, that they had a finite number of outcomes, and assuming that the game is fair. For example, if you toss a coin, so you assume that it is a fair coin. If a die is thrown, then you consider that it's a fair die, etc. If it's a pack of cards, then you assume that it's a pack of well shuffled cards, 52 cards. So these assumptions seem to be valid there, that is exhaustive, mutually exclusive and equally likely, and therefore this definition was given, and this is the one which is used in the calculation of the probabilities in the classical examples. So main disadvantages, or you can say drawbacks of this definition, are that n need not be finite. For example, if we are considering the number of trials needed for the first success, then we do not know when we will stop. Suppose we are considering life of a bulb, suppose we are considering weight at birth of a child, then all of these outcomes, the collection of outcomes is an either countably infinite or uncountably infinite set. Then second is the more crucial thing, that we are saying that the outcomes are equally likely. Now equally likely thing means that we are knowing that the coin is fair, or the die is fair, or the pack is well shuffled, etc. But that is bringing in an inherent understanding of the definition of probability, whereas we are actually defining probability now. So it's a circular definition. The definition is circular in nature, as it uses the term equally likely, which means outcomes with equal probability. Similarly, in a given experiment, we may not be able to express the outcomes as mutually exclusive outcomes. We may not be able to exhaust all the possibilities of the outcomes, because the total number of possibilities may be really large to describe. So this definition, though quite useful in the beginning of the development of the subject, has its limitations. Later on, a more important, or you can say a more practical or a more applicable definition was developed, which we call relative frequency definition of probability, which is based on actual conducting of the experiment. So we can also call it empirical, because it is based on the actual observing of the outcomes, or statistical definition of probability. The form of this definition is due to von Mises. Suppose a random experiment is conducted a large number of times independently under identical conditions. Let an denote the number of times the event A occurs in n trials of the experiment. Then we define the probability of the event A to be limit of an by n as n tends to infinity. Provided the limit exists. Let me give an example of the actual application of this definition. Let us consider, say, a trial of conducting tossing of a coin, and we want to find out the probability of head. So, this we are doing because we do not know whether the coin is fair or not. In the classical definition, we assume that the coin is fair, and then we try to find out probability of head or tail, etc. But suppose I do not know that a coin is fair, I actually want to find out the probability of head. Suppose an experiment of conducting of tossing of a coin results in 2 heads followed by a tail. Now, let us look at the sequence an by n here. So, the sequence an by n here, if you make it, in first trial you have a head and we are interested in the occurrence of head. So, an by n is 1 by 1. In the second trial again there is a head, and therefore, the ratio an by n is 2 by 2. So, we are looking at the event is occurrence of head. So, if I look at the third trial, then in the third trial tail has occurred. So, the occurrence of head is 2 and the total number of trials is 3. Now, if we just continue in this direction, we can write the sequence an by n like 1 by 1, 2 by 2, 2 by 3, then it becomes 3 by 4, 4 by 5, 4 by 6, etc. And now, in order to calculate the probability of head, we need the limit of this particular sequence. So, in order to do that, let us write a proper mathematical expression for this. We can write it as, say, 2k minus 1 by 3k minus 2 for k equal to 1, 2, etc. We may write it as 2k by 3k minus 1 for k equal to 1, 2, etc. If the number of the trials is of the form 3k, then it is 2 by 3. 2k by 3k for k is equal to 1, 2 and so on. So, in each of the cases we are able to describe the ratio an by n, and it is very obvious now that if I take the limit of this as k tends to infinity, that is n tends to infinity, then the limit of this is 2 by 3, and therefore, probability of occurrence of head is 2 by 3. That means, it is a biased coin in favor of head. Now, the relative frequency definition seems to be the one of the most reasonable definitions of probability, in the sense that it is based on the actual experience, and that is what the subject probability should be all about in terms of statistics. For example, if we are looking at the age at death of a person, then it should be based on the experiment, that is really how many people survive beyond the age 60, beyond the age 70. That means, it should be based on the recorded age at death for the various persons. If we want to find out the sex ratio in a population, then we should look at how many children are born as male and female. So, it should be based on the actual data. If we want to say something about the rainfall, then we should know in the past 10 years or in past 50 years what is the pattern of the rainfall during monsoon season. Therefore, this relative frequency definition seems to be the most useful definition for calculation of the probabilities. However, even this definition has certain drawbacks. For example, we are making an assumption that the experiment is observed, but there may be certain experiments where we may not be able to look at the observations. The observations may be less in number, or they may be too complex, too complicated, too costly. For example, if we are looking at the failure rate of launched satellites, then it is not an experiment which can be conducted every day. And if we are looking at from a country like India, then the overall launches of the satellite itself may be limited to a very small number, and therefore, in order to find out the probability of a successful launch may be quite complicated. Although we are not saying that this type of calculation of probabilities is impossible, but it is difficult certainly if we want to look at the full experiment. However, the probability can be calculated using certain rules of probability by splitting the entire launch of satellite into various sections or various segments, and then we combine the probabilities of those various things. So, the actual conduct of the experiment or actual observation of the experiment may not be possible sometimes. Also, there are certain experiments which are destructive in nature. For example, we want to look at how many of the matchsticks kept in a matchbox are useful. So, conducting of an experiment means that we actually light a matchstick and observe whether it is giving good result. That means it burns, the full stick burns, etc. So, this kind of experiment is destructive in nature because it will lead to the destruction of the material itself. And similarly, there are various experiments conducted to test the strength of the materials. Then it means that you apply a certain pressure on the material which is used for making of certain mechanical things such as say a car or an engine or a train line. So, the strength of the material is very important. However, the testing requires that you put some compressible force on that and observe it to break at a certain force, and then we estimate that how much actual force will be required. If the actual force which is going to be applied on that material is less than the breaking strength, then we say that the material is all right. So, however, such experiments are also costly in nature, and sometimes it is skipped in order and it is replaced by certain other process to measure that strength. Sometimes this probability relative frequency definition may give a result which may not be very intuitive. For example, if I say the probability of an event is 0, then you must feel that the number of occurrences in experiment for that particular event must be 0. However, here since it is taken as a limit, so we may have say root n as the number of happenings in n trials, and if I consider the limit of this, then this is 0. So, although the number of occurrences is not 0, but the probability of the event is 0. Similarly, we may have n minus root n by n, which will converge to 1. So, every time the event does not occur. However, the probability is 1, which indicates that this is a sure event. However, we may treat it as in the sense that it means that the number of occurrences is negligible in comparison to the total number of trials. Again, this may lead to a little bit of confusion. For example, I may consider n to the power say 1 minus epsilon divided by n, where epsilon may be a very small positive number. Now, here again this will go to 0. However, this will not be negligible number. So, now it is negligible in the sense that if I look at the order, then in the terms of order, the order of n is more than the order of n to the power 1 minus epsilon. So, this type of justification can be given for the relative frequency definition. Now, We may now we consider a more rigorous definition of the probability. The first two definitions which I have given, they are based on the you can say basic, they were based on the basic development of the subject of the probability itself. For example, the mathematical definition was developed as a consequence of the interest of some of the gambling houses to know probabilities of certain events, and they contacted the mathematicians of that time, and they looked at the entire thing as a finite set of outcomes which may be equally likely, and they gave the rules of the probability based on that. The relative frequency definition or the statistical definition is similarly based on the experience. So, when people were really looking from the statistical point of view certain events, and they were not necessarily the events of the type where you have only head or tail or coin tossing, etc., then they looked at that how many times the actual event occurs during a certain number of trials. As we have seen that the definitions have drawbacks, and therefore they are not universally applicable. In order that a theory be consistent or universally applicable, we need certain axioms. So, in 1933, the Russian mathematician Kolmogorov, he gave what is known as the axiomatic definition of probability, and this is based on the set theoretic development which we gave in the very beginning, that is on algebra of sets. So, now we describe what is axiomatic definition of probability. What we have is that given a random experiment, we have a sample space, and now certain subsets of omega are the events which may be of interest to us. We may not be interested to consider all subsets of omega. So, what we can consider is, we can consider a sigma field of subsets of omega. So, a sigma field of subsets of omega will consist of certain events, then their unions, their complementations, their intersections, their differences. In other words, if we are considering certain events, then all the manipulations of those events which are of interest to the experimenter will be included in the set V, and therefore, this definition of sigma field is useful in development of this definition, or you can say axiomatic definition. So, given a random experiment, we are considering a sample space and B a sigma field of subsets of omega. That means, in the terminology of probability theory, this is a set of events. So, omega B is called a measurable space, and now we are interested to define the probability. So, for every event which is included in B, we must be able to define the probability function. So, the axiomatic definition of probability, it is due to Kolmogorov. Let omega be a probability, be a measurable space, a set function P from B to R is a set of real numbers, is said to be a probability function if it satisfies the following three axioms. I will call them P1, that is, probability of A is greater than or equal to 0 for all A subset of B. The second axiom is that the probability of the sample space is equal to 1. The third axiom is that for any sequence of pairwise disjoint subsets EI belonging to B, probability of union EI is equal to sigma probability of EI I is equal to. This last axiom is known as the countable additivity axiom. The first axiom is known as non-negativity axiom, and the second axiom is known as the axiom of completeness. So, we will continue from here. We look at the properties of the probability function, which is given by the Kolmogorov definition in the next class. Thank you.